15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello, and thank you for joining us on another edition of the Space Nuts podcast, episode 172. My name is Andrew Dunkley, your host if you're joining us for the first time. If you're joining us for the 172nd time, I'm sorry I've said my name 172 times. And with me, as always, for the 172nd time is Professor Fred Watson. Hello, Fred.
Hey, how are you doing, Andrew?
I'm good. The question is, how are you, you jet-lagged fool?
Not sure. Bits of me are still somewhere in the Indian Ocean, I think. But, most of me is here.
Yeah, how was your trip?
The bit that's here is the grumpy bit. So
that's always the bit that gets home first.
Yes.
Now, where did you go?
I had a week in Munich, or in a small town near Munich called Garching, which is where the European Southern Observatory has its headquarters. So there's a very pretty impressive headquarters building and other things there, as well as a rather marvellous planetarium, the Supernova Planetarium, which was only opened last year. And so that's got an exhibition in it. If anybody's ever in Munich and interested in astronomy, that is definitely the place to go. It's a sensational exhibition. The planetarium itself has got a state-of-the-art projector in it. Very, very good. So I was at a conference there talking about education in astronomy, which is something close to my heart and yours too. And then I had the weekend in Rome.
How horrible for you.
It was actually, because I spent most of the time in my hotel room preparing my talk for Monday night at the Australian Embassy, where I had an engagement there. In fact, I had a lovely day of meetings at various very interesting organisations like the Italian Space Agency, ENAF, the headquarters of the Italian Astronomy Research organisation. Also, a company called Telespazio, which is a company that does a lot with the space agency there, and they do some amazing things on Earth observations and things of that sort, and wound up with the Nuclear Physics Research Institute, where they're actually collaborating with scientists here in Australia, in Melbourne, to build a dark matter detector in a disused mine at a place called Stoyle, which is between Melbourne and Ballarat. So all that was very interesting. But another highlight, which would really only be of any interest to Australian listeners, I think, is that on Sunday morning I was at a memorial service, not in the Vatican, but not very far away, for Tim Fisher, the former Deputy Prime Minister of Australia.
Yeah. Amazing bloke. I met him a couple of times, interviewed him a couple of times over the years. I have never come across a politician who genuinely came across as a true gentleman. That he stood head and shoulders above so many people in such a ruthless game as politics, and he just always seemed like your best mate. He was just a fabulous guy.
Yes, he's somebody I was very sorry never to have met, because I would love to have talked about trains with him, because he was a train enthusiast as well.
Yeah, he loved his trains.
Yeah, that's right. But he, towards the end of his life, he was actually the Australian ambassador to the Holy See, which is why there was a memorial service for him in Rome. And so it was an honour to have been invited to attend that, and as a guest, actually, of the present ambassador to the Holy See. So that was very good and very moving, and very
fitting. Yeah.
Very fitting for a great man. He was a great man.
Yeah, quite an honourable bloke. Now, speaking of the Australian government, one of the things we'll be talking about today is Australia's gift to NASA, which has gone down like a lead balloon in the local media, I might add. We've previously talked about Tabby's star and the mystery surrounding the reason that it sort of dims and then doesn't, and then it dims again, and now they have a theory. We also look at Venus could it have once been habitable, and what went wrong? I suspect the occupants of Venus burnt fossil fuels for a couple of hundred years, and then all hell broke loose. Not that that's going to happen here. And we'll answer some questions about gamma ray bursts, gravitational waves and their effect on atomic clocks, and whether or not a blue shift indicates a universal collapse. Somebody's got plenty of spare time or is just really, really worried about the future. We'll get onto all of those very, very soon. But what have we given to NASA, Fred?
Oh, it's that's the interesting bit, because yes, it's a gift to NASA of $150 million spread over 5 years from the Australian government via the Australian Space Agency to support NASA's plans for trips to Mars in the end, and of course the Moon as well, which is regarded as a stepping stone to Mars. However, interestingly, yes, it's a gift to NASA, but really it's a gift to Australia, because the deal, I think, means that most of that money will probably come back to Australian industry. So it's all about engaging Australian industry to support NASA with technology and with some of the ideas that are needed to bring about exploration in NASA. There's a headline I read today about some of the autonomous vehicles that are used in the mining industry have. They've got characteristics that might be useful in developing vehicles that might be able to explore Mars. I mean, NASA's got a pretty good track record on that, with 3 very successful rovers. In fact, 4 if you include, I think it was Pathfinder.
As against Indica, but that's another story.
Well, yeah. But no, that's right. I mean, I think it's an interesting area of research, and I think it is actually a good thing that we in Australia are visibly supporting NASA's NASA's work in that. It is, of course, only 0.7% of NASA's annual budget that we've given to them, but that's all right. That's still going to make a difference.
Of course, and of course, the negative press that sort of came along with this announcement is obviously based on very narrow focus. Why aren't you putting that money into the drought instead, et cetera, et cetera. But we've got to be there for the future. Yeah. We've got to be involved in space travel and space exploration and space industry. Otherwise, we're going to be a very lonely country in the long-term future. So, in the scheme of things, $150 million, not a lot out of our budget either.
I think one of the one of the telling statements came from Andy Thomas, Australia's first astronaut. Actually, he wasn't Australia's first astronaut, but that was Paul Scully Power. But a well-known Australian astronaut, now retired. And Andy made the point that he's been a big supporter of the Australian Space Agency, was instrumental in getting it going, instrumental in the fact that it's going to be based. Its permanent base will be in Adelaide. It's currently based in Canberra, but will move to Adelaide probably around the end of the year. But his comment was, it's great to see the space the space agency engaging with human space flight, because most of what we do in Australia in the space, in terms of space presence, is about scientific and industrial applications, but not necessarily human spaceflight, whereas this is definitely directed towards that goal. So it's expanding the horizons of the space agency in, I think, quite a good way.
Good stuff. All right.
Yeah.
Now, let's move on to Tabby's Star. We've talked about Tabby's Star before. It's an unusual situation because it has this strange habit of dimming, and they haven't really been able to understand why. Now, this is a star we've known about for a long time, but now they seem to have come up with a possibility as to what the answer is here, Fred.
Yeah, that's right. Some work that that goes perhaps puts another block of stone in the edifice of our understanding of this object. We should give it its proper name, which is KIC 8462852.
You just love doing that to me.
Yeah, only when it's written down in front of me. Often known as Boyajian star. I'm not sure whether I'm pronouncing that correctly, but it was Tabitha Boyajian who noted the curious behaviour of this star, which is basically on. It's very unusual fluctuations in its light. So it came out originally from the Kepler Space Telescope program, which was looking for the dimming of stars caused by planets passing in front of their parent stars. And we, as you and I have spoken about many times before, that's netted the current total of just over many of the current total of just over 4,000 known planets around other stars. There are other ways of detecting them, but the so-called transit method, which is what Kepler has done, actually is the one that has been the most productive. It's been an eminently successful way of detecting planets, and Kepler now has a follow-up mission called TESS, which is doing a similar job in the whole sky. So Tabby's star is in the constellation of Cygnus. It's it's getting on for 1,500 light years away as the crow flies, so it's not a nearby star. But what marked it out was these very unusual fluctuations in its brightness, not the kind of thing that you would get from a planet passing in front of it, which would, a Jupiter-sized planet passing in front of the sun drops its light by 1%. So that's the typical sort of thing that you're looking for when you're looking for extrasolar planets. But Tabby's star drops it by up to 22%, which is huge, and does it in a peculiar way. It's not a planet, is it? Planets aren't blocking the light. That's something is blocking the light, but not planets. And I think my recollections are looking at previous work on Tabby's star that there is a sort of quasi-periodicity. By that I mean that that the drops in brightness, whilst they're not strictly periodic. By that I mean with a regular frequency. They're vaguely periodic. Can I put it that way? Mm-hmm. So. Although they vary, I think the 22% one was a one-off. And the other thing is that astronomers have looked at measurements of the brightness of this star over very long periods of time, because what you can do when you know that you've got something interesting there, you can go back to archival photographic plates taken over the last 100 years or so and look at how its brightness has changed, if it has, or how its brightness has held up. And it turns out that this star has faded in brightness by, I think it's 14% over about the last 100 years, and that in itself is a curious phenomenon that doesn't really seem to be explained by the astrophysics of the star itself, which is actually a similar star to the Sun. It's actually an F-type star. Okay. Sun's a G-type star, but it's similar, a similar type of star. So people have proposed all kinds of things like swarms of comets. One that I think you and I might have talked about is the possibility of a Dyson sphere being erected around the star. A Dyson sphere is a hypothesized edifice that's put around a star by an alien civilization to collect all the light, all the energy from the star. So that was another suggestion. I think that's probably at the far end of the hypotheses. It's only now, though, that I think a reasonably coherent picture of what might be going on has been put forward. And it's come from a group of astronomers who, if I remember rightly, let me just check where they are. They are at Columbia University, which is an interesting place because they're going to be the publishers of my new book when it comes out in the United States. Just as a plug there.
Why not?
Exploding Stars and Invisible Planets. It's not called that in Australia, but that's all right. So astronomers at Columbia University have built this model of what would happen if you had not a planet in orbit around the star, but the moon of a planet that has been pulled away from its parent planet by the star's gravity and is being destroyed basically by the star. And it turns out that all the numbers add up if you've got this situation that this basically you've got a moon that is falling to pieces, it's evaporating, and the kinds of dimming of the parent star that you see match what you would get from this model. So it sounds like a fairly complicated construction, the theory that's led to this, but it seems to be that it does fit all the pieces. Actually, one of the authors says, let me just say, he's actually one of the researchers working on this. Says the team's model is unique in its hypothesis of what drives the original planet towards the star in the first place. So the planet itself is also being disrupted. And it naturally results in the orphaned exomoons ending up on highly eccentric, which means elongated, orbits with precisely the properties previous research had shown were needed to explain the dimming of Tabby's star. No other previous model was able to pull all these pieces together. So this model, for all it seems a bit contrived, actually fits the data.
Yeah.
And that's the good thing about it. So it suggests that it's this exomoons, and an exomoon, of course, is a moon around an exoplanet, a planet around another star. It's got this dusty outer layer of ice, gas, and perhaps carbonaceous rock as well, and basically this is all forming a disk around Tabby's star and giving us these peculiar variations in brightness, including, as the dust builds up, a dimming of the star itself over a long period of time.
Yeah. So, as the dust thickens, the light gets held back bit by bit by bit, and it reduces the amount of light we detect. Yeah, it makes perfect sense. It's a simple explanation in the end of things, isn't it?
That's always, you always apply what's called Occam's razor, which is to make the simplest explanation possible. And whilst this is a complex one, it's nevertheless simpler than what we've had already.
Yes, indeed. All right. Well, I'm sure there'll be more to learn once they get the data together on Tabby's star. But it does sound like they're right on the money with the explanation. You're listening to Space Nuts. Andrew Dunkley here with, of course, Professor Fred Watson.
Roger, you're loud and clear here also.
Space Nuts.
Now, before we move on to the next topic, Fred, just another shout out to say thank you to our patrons. We're getting more and more people signing up to Patreon to support Space Nuts. We so much appreciate that. And, of course, as a patron, you will have access to the commercial-free version of the show. I know some people get that anyway. It depends what part of the world you're in. But that's one of the benefits, and we're slowly putting together other benefits, which we will let you know about down the track. So thank you for signing up to Patreon. You can do that if you would like to support the program at patreon.com/spacenuts. As I've said before, it's not mandatory. We're not going to crack you over the head if you don't. It is a certain, it's certainly an option, and it's totally up to you. But thank you to everybody who has supported us through patreon.com/spacenuts. It won't go unnoticed, and we really appreciate your support. Now, Fred, we are going to talk about the planet Venus. Now, this is a place that's hideously warm, has got an outrageously out-of-control greenhouse effect going on, but now a new study suggests that at some stage in its deep, dark past, it may have been habitable until something horrible went wrong. I'm thinking, inhabitants burning fossil fuels, but I could be wrong about that. What's the story behind this? This is fascinating.
It is. It's some very interesting modelling of Venus that has been done with some, as you said, some quite surprising results. So yes, Venus is closer to the sun than we are, but that is not the full story when it comes to explaining why Venus is so much hotter than the Earth, because with a surface temperature in the region of 450 degrees Celsius, it is quite a lot hotter than the Earth is. And that's all about the greenhouse environment that that Venus is in. In other words, its atmosphere. So Venus's atmosphere, like the Earth's, has nitrogen in it, but is also richer in carbon dioxide than the Earth's. And so it traps the heat, and the surface temperature rises enormously, and that then comes with all kinds of very peculiar effects on the atmosphere. Things like the sulfuric acid drizzle that happens at high layers in Venus's atmosphere. It does make it a place that you shouldn't put on your bucket list for a holiday. So why is it like that? Well, there's a greenhouse, a runaway greenhouse effect, exactly as you've said. But I think what's interesting about this piece of research is that people have actually really started seriously looking at why that should have been. What was it inevitable that would happen with a planet that is nearer to the sun than the Earth is? And the answer is apparently not. What this group of scientists have done, and these are people who are based at NASA's Goddard Institute for Space Studies, so it's not, they're not fly-by-night astronomers or anything like that, although most astronomers are fly-by-night, I guess they have to be by definition. So they're looking at, they've looked at the things like the topography of Venus, the actual structure of the surface. They've looked at what we know about volcanism on Venus, which is that it was, in fact, we know Venus actually has more volcanoes than any other body in the solar system. So it has had a very active volcanic past. But they've also looked at the kind of phenomena that we know stabilizes the Earth's atmosphere. And what is a key to the Earth's atmosphere being stabilized is actually plate tectonics, as I think we've discussed before. The fact that plate tectonics is a means of getting carbon dioxide out of the atmosphere and into the crust of the Earth. It basically, the carbon dioxide either goes directly into the oceans or turns into carbonic acid and is absorbed that way. But either way, it eventually finds its way down to the seabed, and you get carbonaceous rocks building up. And I mean, I'm talking now about geological time. That is then subducted under the continental plates, and that is a great way. Some of it comes back up through volcanoes, but it nevertheless stabilizes the carbon dioxide content in the Earth's atmosphere. And so what the modelers who have done this work have built into their idea is that Venus actually was a world similar to the Earth for most of its history. Plate tectonics did their thing, kept the atmosphere at a perfect level. They had surface liquid water, perhaps a stable climate, very much like that of the Earth. And then they speculate that maybe 1 billion years ago, or perhaps 700 million years or something of that sort, something happened to change that. And they run a whole lot of hypothetical scenarios in their modeling and come out with something that actually fits the bill rather well, which is for a 700 million year ago event that would have basically stopped the plate tectonics in their tracks and stopped this this carbon dioxide sink. And what they're suggesting is that some sort of volcanism probably released a huge amount of gas into the atmosphere of Venus, and effectively, that gas basically was produced by some intense volcanism, which together with this highly gaseous envelope also sort of sealed up the surface with what would have been molten magma, but then solidifying on the surface and stopping the plate tectonic cycle.
And that happened at a global level.
At a global level, yeah. So there's something really very, very significant, nothing like the kind of things that, for example, we know that there was 500 million years ago on Earth, there was large-scale outgassing into the atmosphere from volcanism, which produced something called the Siberian traps, which I think, if I remember rightly, they're lava flows. And there was a mass extinction as a result of that. But that's, small beer compared with what evidently must have happened on Venus, perhaps around about the same time or a bit earlier, in order to produce what we see today, which is a planet with a runaway greenhouse effect. It's a really interesting idea. that you are once again relying on modelling to get this impression of a nice temperate Venus before this event happened, but it is it's based on fairly solid research, so it does have a lot going for it, particularly when it's written by people who are in one of NASA's actually most eminent planetary sciences institutes. So
that is amazing, and one wonders what it would have been like as a habitable world if it was not dissimilar to Earth in terms of its topography and water and oceans and that sort of thing. What compared to us, what would it have been like?
Well, it would have been much the same, but with the sun slightly bigger in the sky and maybe rather warmer. They're suspecting that the surface temperatures might be higher than what they are on Earth. They're talking about 20 to 40 degrees Celsius on average for the whole planet, whereas here on Earth, the average temperature, I'm pretty sure it's 15 degrees Celsius, the average temperature for the planet. So that's putting it into Fahrenheit terms. That 20 to 40 degrees is, of course, 68 Fahrenheit, which is the 20 degree mark, to about 104 degrees Fahrenheit.
So
which is
the extremes would be much higher in some.
So it would have been hotter, but you're still only talking about temperatures like what we get in Australia at times.
Yeah, very true. Yeah, it sounds like it would have been quite a livable place. So one now wonders, assuming their theory is spot on, whether or not Venus did have life.
Yeah,
at some stage.
So maybe one day we will have the wherewithal to explore Venus robotically. I can't imagine we'll ever walk on the surface of Venus with those temperatures, but who knows what sort of things we might find with a robot strolling around Venus. Oh, here's a fossil. Oh, there's another one. Yeah. Although, if you've got super volcanoes sealing the whole surface with magma, there's probably not going to be much left of the fossils that you might.
I suppose not, but they'll probably find the smoking gun in 1970s Cadillac. That'll be the reason. That's what happened. No, it is fascinating, quite amazing, and that sort of makes you think. Well, hey, hang on a second. If that happened at Venus,
yeah, exactly.
And we look at Mars and go, well, at one stage Mars had possibly liquid oceans, and here's Earth. I mean, hello, suddenly there are 3 potential livable planets in our own solar system.
And only one left.
Yeah. And we're messing it up.
Yeah, that's right.
Okay, well, there'll probably be more on this not far down the track, so we'll keep an eye on that story as well, because it's well worth reviewing. You're listening to Space Nuts, the podcast with Andrew Dunkley and Fred Watson.
0G, and I feel fine.
Space Nuts.
Now, I did send a shout out earlier to our patrons through patreon.com. I'd also like to send a shout out, Fred, to our YouTube followers. We're starting to build quite a little audience in YouTube. We've got 278 subscribers that now listen via YouTube, which is wonderful. We've decided to set a target. So we would like to reach 1,000 because apparently that's a good number. I don't really understand YouTube and how the numbers work, but getting to 1,000 is something that benefits benefits YouTube, obviously, but also benefits Space Nuts. So we'll push on. So if you'd like to become a subscriber to Space Nuts via YouTube, just do a search in your YouTube app or whatever it is you use, and add yourself to our growing list of subscribers on the YouTube Space Nuts channel. That would be fantastic. Now, we've got some questions to get through, Fred. We've got a few today. A couple will be easy and one will be easier or maybe harder. I don't know. This one comes from Bentley from Boulder. Bentley from Boulder. And I'm sure he doesn't have an accent like that because he's in Colorado. To the dynamic duo, Andrew and Fred. Oh, that's the first time we've been called that. And it will be the last time. Would blue shifting light from distant galaxies be a sign that the universe is beginning to collapse back on itself, i.e. the big crunch, or to slow down the big freeze? That's a really interesting question. Light gives a lot of, the light spectrum gives a lot away when you're making observations in space. So what would a blue shift indicate, Fred?
Well, it would certainly tell you more than that the universe's expansion was slowing down, because in order for the light from a galaxy to be blue shifted, the galaxy's got to be coming towards you. So you're already in a scenario where the universe is collapsing if you see blue shifts. We do see blue shifts actually for a few nearby galaxies where the individual of the motion of the galaxy is enough to overcome the expansion of the universe. Excuse me, beg your pardon. It's really only when you start looking at relatively distant galaxies that the expansion of the universe is the most the most obvious feature of the spectrum, and so you get the redshift. So there are blue shifted galaxies, but they're in fact what we distinguish between is something called the Hubble flow, which is the speed of a galaxy as a result of the expansion of the universe, and something called the peculiar motion, which is the motion of a galaxy that's peculiar to that galaxy, and might be caused by the fact that it's got a nearby neighbor, like we have with the Andromeda galaxy, and they're pulling together gravitationally. That will be enough to overcome the redshift, because the distance between these objects is small. So we do see blue shifts, but not on what you might call a cosmological scale, not in the wider universe. We only see redshifts. So there's no danger that suddenly we're going to wake up one day and find all these galaxies that hitherto have had redshifts have now got blue shifts. That's not going to happen. But in a different universe from ours, one with more mass in it that would cause it to collapse on itself, yes, that's what you would see. You would see blue shifted galaxies. So a good question, and thank you, Bentley, for that.
Could the expansion of our galaxy, of our universe, be pushing another one back in on itself? Is that?
Who knows? That's right. Yeah. I mean, there are ideas that ours is just one of many universes, and maybe they are all jostling for some sort of hyperspace and nudging one another out of the way. But that is at the moment beyond the realms of anything that we can actually do in terms of observational discovery. All you can do is speculate, and our speculations, I think, Andrew, are as good as anybody else's.
Yeah, I'll take it.
Yeah.
Okay, thanks, Bentley. Great question. Now we've got a question from Christopher Pooley. Christopher's messaged us and had a question on before. So he has another one that we thought we'd tackle. So Professor Google and her research assistant YouTube tells me that gamma rays cannot penetrate our atmosphere. However, a lot of scientists feel that a gamma ray burster could sterilize large amounts of planets in a given galaxy, assuming they have life. They told me that a gamma ray burst is a spinning supermassive star that is collapsing and turning into a black hole, the source of some of the biggest explosions in the universe. My question for Andrew, I thought I'd read that bit. For you, Fred, is Google right? Does our atmosphere protect us from gamma rays? If so, what about the gamma ray burster? Would it be that these scientists think could turn Earth into a post-apocalyptic wasteland? Love the show. Keep it up. Chris, that's exciting, isn't it?
It is, yes. So the answer is yes. If you've got a gamma ray burster which is directing its gamma rays at the Earth, and it's not very far away, it strips the atmosphere of all its electrons, and suddenly you've got nothing that's breathable, and things start getting pretty bad very quickly. Well, the reason why we know about gamma ray bursters is interesting in itself, because they were not known until I think it was the 1970s, when various nuclear protection treaties were enacted, global treaties banning atmospheric nuclear tests, and they were monitored by a fleet of small satellites which were designed to pick up the gamma rays from anybody who broke the law by detonating a nuclear weapon in the atmosphere. And what these gamma ray satellites found was not stuff coming from the ground, but stuff coming from space. They detected occasional blasts of gamma rays, which were, very mysterious for a long time. In fact, I guess it's fair to say that it's really only been in the last 10 to 15 years that astronomers have understood the mechanism by which gamma ray bursters work. And it's more or less, as Christopher says, that if you've got this highly massive star maybe a neutron star that's spinning, and something happens to it that causes it to collapse into a black hole, then you get this huge burst of energy, which doesn't last very long. It's a matter of, I think the gamma rays are over in a matter of seconds to minutes, but often there is an optical flash, a visible light counterpart, and that's actually very useful if you can see that to work out how distant these things are. And we know that they are at great distances; they're in very distant galaxies. So for a while, and I think this work still goes on, there was a system set up whereby if a gamma ray was detected by one of these special gamma ray detection satellites, then you alert the optical and radio astronomy communities and get them to point to the place where the gamma ray burst came from to see if there's any afterglow. And that has happened, and it's been detected. And that's how we know a bit more about the physics of these things. The fact is that these gamma ray bursters that have been observed are all a very long way away. So the gamma rays are pretty weak by the time they get to the solar system. But if you did have one in our galaxy, and its jet of material was directed in the right direction, its jet of highly energized radiation was in the right direction, then yeah, we could be fried. It could strip the planet of its atmosphere. So I think the answer is that both Google and YouTube were right.
Okay.
Yeah.
Gee, thanks, Chris, for giving us one more thing to worry about. Really appreciate it. But no, it is fascinating. The odds are very, very minuscule, though, aren't they?
Yes, they are. They're very slight. There's, I think, we've discussed a star recently.
It rings a bell.
Most of my brain is still over the Indian Ocean, so I can't remember it. But I do remember that this was a candidate in our galaxy for a possible gamma ray burster. It might be Eta Carini, actually, which is a very large and unstable star. But it turns out that the axis along which the gamma rays would be directed is not actually pointing at us. So we might survive if it does go off.
Phew.
Yeah,
okay.
phew.
Thank you, Chris, for your question. We'll move on to the final question for this episode from, well, it's a double bunger, because I think this was a discussion that was on the podcast group on Facebook. And someone asked a question and someone else responded to it. So I'm going to credit both Damien Huxley and Brett Campbell for this one. They say, I wonder if Andrew Dunkley can ask Professor Fred, how does the maths work when looking at gravitational time dilation? If everything else is the same for both planets except for the mass, one is Earth, the other is 100 or 1,000 times bigger, what is the change in time? If you were able to watch all the atomic clocks on the GPS satellites as a gravitational wave moved past, would the clocks change time? Very, very good question. I love time questions and dilation questions. I really think this is good stuff.
It is good stuff. So, and we actually have had another question, which is very similar to the second part of this one. We had another question about atomic clocks detecting gravitational waves. So the question we've got here is as you said, it's a two-component one. What's the change in time for when mass goes up by a factor of 100 or 1,000? I don't know the answer offhand in terms of the mathematics, but it's relatively straightforward. When you look at the equations of general relativity, they are a bit horrendous in that there are things called metrics which involve matrices of large amounts of numbers. And it all goes into something called tensor calculus, which between you and me, Andrew, and I hope nobody's listening to this, I've never really understood, probably because I've never really read it up properly. But what often happens is these things boil down to relatively straightforward equations. So, sometimes it's just a question of proportionality, although there's usually the speed of light involved in there somewhere, which is a constant raised to some enormous power, often c to the fourth, when you look at gravitational, the disturbance of space by gravitational waves. So I can't give an answer to how much the time dilates how different it is from one planet to another, except to say that it is gravitational time dilation because of the Earth is actually a very small amount. You're talking of probably nanoseconds, that kind of level when you compare, and people have compared clocks in aircraft and clocks on the ground and clocks in satellites and clocks on the ground, and it's certainly measurable, with modern technology. But how different it is from one planet to another, I don't have that number at my fingertips. I'm actually, in some ways, more interested in the second part of the question, which is if you were able to watch all the atomic clocks on the GPS satellites as a gravitational wave moved past, would the clocks change time? And I guess because gravitational waves are a distortion of space-time, the answer is yes. But I think the numbers would be infinitesimal compared with what we can detect now. There's a related question from Damien Huxley, which is, and he talks about, cesium clocks and strontium clocks with these very, very high frequencies, but I don't think they're anywhere near high enough to detect the change in time caused by a gravitational wave. That's an opinion pulled out of the air from what I know about the effect of gravitational waves on space, which is, absolutely tiny. It's exactly as you and I have spoken about before on the LIGO experiment in the USA, these 4 kilometer long interferometer arms, they are capable of detecting a movement of the mirror of 1/10,000th of the diameter of a proton. And that is, it's just astonishing. It's about 10 to the minus 19 meters.
Good grief.
And so any equivalent time distortion would be at a similarly infinitesimal level. And I am pretty sure, although I will check this because I know people in the time world, I will check it, but I'm pretty sure that we have no way of detecting the kind of change that would occur as a gravitational wave passed.
There you go. Well, we managed to knock off 47 questions in one there, I think, which was good. We've caught up now. We've got none left.
Yeah, that'll be the day.
Yeah.
I think we've still got enough to keep us going for about 5 years, Andrew.
I suspect so, yeah. But thank you to everybody who asked all those related questions. Much appreciated, and hopefully the answer was... they ask questions because they don't know the answers. So, but they might have had some theories. But yes. maybe we help fill in some blanks for them, Fred. And thank you. It's always a pleasure. We covered a lot of ground today and some really fascinating topics as well. So thank you very much. As jet lagged and dazed as you are,
I'll of course will not remember any of this conversation in 10 minutes. So
it's a good thing I recorded it.
It is just as well, yeah. Thanks a lot, Andrew. Good to talk to you, and we'll speak again next week.
We will indeed. Professor Fred Watson, astronomer at large, joins us every week here on Space Nuts, as do you, and keep spreading the word. The more the merrier. And we will catch you next time on another edition of Space Nuts.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Subscribe to the full podcast on iTunes and Stitcher or your favourite podcast distributor.
This has been another quality podcast production from Bytes.com.